we take a look at the regularized regression and try to understand the purpose of regularization in different problems. Let us begin with the recap of the least squares problem. Let us consider the simplest instance of least squares, that is the curve fitting problem in one dimension. Let us say that we are given some points ui, yi for I equal to 1 to n. And let's say that we want to find the curve that passes through these points. So if ui is one dimension, then the curve would be passing through ui, yi points in two dimensions. So the standard approach for curve fitting is to find the best fit solution, that is the curve that best fits the given points. Mathematically, if this curve is described by a function f, then the goal is to find the function f that minimizes the mean squared error between yi and f of ui over all I between 1 and n. Generally, however, we do not want to search over all possible functions f, but instead restrict our search to smaller classes of functions. For instance, in parameterized learning, the class of functions that interest us are those that are fully specified using some reasonable number of parameters. We get the classical least squares problem if the function depends linearly on the parameters. For instance, if the function is specified as u transpose x or u transpose x plus u transpose u times xn plus 1 plus xn plus 2. In both these cases, the function f depends linearly on the parameters or the parameter vector x. It is possible for the least squares problem to be ill-conditioned. Suppose for simplicity that we are considering the linearly parameterized function class, so that the least squares problem is written as min over x 1 by n summation I equal to 1 to n norm square of yi minus ui transpose x. We know that the problem may be ill-conditioned, for instance, when the number of points n is less than the number of parameters small n. Intuitively, you can imagine that if the goal is to estimate small n number of parameters, then we expect the number of observations capital N to be much larger than this small n. So when capital N is less than small n, then there are infinite number of solutions. In fact, you may recall that the solution to y equal to ux takes the form x equal to wv plus x naught, where the columns of w are in the null space of u. In other words, the set of solutions is an affine set. Recall that one of the solutions is given by the pseudo inverse of u times x. Now the fact that there are infinite number of solutions is not an issue mathematically, but from a practitioner's perspective it raises the question as to which of these infinite solutions do we really want for our application. Another implication of having the ill-conditioned problem is that it has poor generalizability or the inability to handle unseen data. In fact, generalization issues start popping up even when n is not much larger than small n. To see this, consider the one-dimensional fitting problem again. Let us say that we are given capital N equal to 10 points. In the function class that we are interested in is the class of 8th degree polynomials. Recall that 8th degree polynomial would have 9 parameters in total, so small n is equal to 9. Therefore, the least squares problem has a unique solution. As you can see from the curve fitted here, because it is an 8th degree polynomial, it fits almost exactly with the given points with very little fitting error. The residual error or the training error, which is the error incurred in the training process, is very small. It is 0.0042. But there is a downside to fitting a curve so precisely, which is that the curve becomes very wavy. The reason curve is so wavy is because the 8th degree polynomial is so expressive that it can actually fit the given points almost exactly, but at the cost of yielding a complicated curve. This is called overfitting, and a classical symptom of overfitting is that if you evaluate the error on new observations, it would come out to be very high. In this case, the error on new observations is coming out to be 0.27, which is much higher than the training error, almost 100 times higher. So in summary, whenever the number of parameters that describe a curve are very large, relative to the number of observations, there is a possibility of overfitting, wherein the test error, which is the error evaluated on new observations, becomes much larger than the training error, which is the error evaluated on the given observations. So even though we have solved the least squares problem correctly, in the ill-conditioned or poorly conditioned case, we see overfitting. It begs the question if there is an alternative formulation we should have used. In other words, was the least squares the correct problem to solve in this case? As students of optimization, we are not only interested in solving the given problems, but also in formulating them so as to obtain the desired result. An alternative formulation is the so-called regularized least squares, which yields the black curve that is shown here. You can see that the training error of the black curve is much higher than the training error of the blue curve. And in fact, the black curve does not even fit properly. On the other hand, the test error here is less than half of what the blue curve gives. So this is a simple demonstration of the fact that sometimes higher residual is also okay as long as we get a lower test error. The extra error in the residual or the training error then gets attributed to the noise that may be present in the data. In other words, we are saying that the reason the black curve is better but does not appear to fit the given observations exactly is because the original observations that are given to us are noisy, and when fitting the black curve, we are aware of this fact. So the regularized least squares is able to reject the noise. Of course, the new points may also suffer from noise, and that is why the test error will not go to 0. Let us then look at the process of regularization. We will motivate it from the Bayesian perspective. If you are familiar with the Bayesian perspective, you may know that we postulate that the data or observations ui, yi are random and independent, identically distributed. We can assume that the observations are arising from some unknown PDF p of u, y. For instance, even if we are looking at some images and their labels, we can say that those images and labels are actually samples that are drawn from an unknown distribution. Now, what we have been doing so far is that we have been focusing on the problem to minimize the mean square error, which is written like this. But if ui and yi are arising from a distribution, then what does the average of the squared error over I from 1 to n represent? Recall that in statistics, if you want to calculate the expectation of a random variable whose distribution is not known, then one way is to draw a lot of samples of that random variable and then calculate their empirical average. Right? This is the empirical mean. So that is exactly what is going on here. We are using the empirical average of the loss instead of the expectation of the loss or risk, because we do not know the PDF p of ui, yi. Summarizing, ideally we should have been minimizing the expected loss, but since we do not know the distribution, we have settled for the empirical mean of the loss calculated over the training data, because as you can see, the expectation requires you to know the distribution p of u, y. This brings us to the question if the empirical loss is really a good replacement for the mean loss or the expected loss. Recall that the law of large number says that it is indeed good approximation if n is large, but of course not if n is not large. Further, how large n should be so that the law of large number kicks in is also problem dependent and is not universal. For instance, in the case of linear regression or least squares, we know that we require capital N to be large relative to small n, which is the number of parameters. In general, n should be large relative to the model complexity of the function f, which may or may not correspond to the number of parameters we have in the optimization problem. For instance, in the case of polynomial fitting, the model complexity is the degree of the polynomial, which has a direct relationship with the number of parameters. For example, a degree 1 polynomial is simply a line described by 2 parameters. On the other hand, in the context of over-parameterized neural networks, it has been seen that the model complexity is not necessarily measured in terms of the number of variables. The demonstration earlier relates to a well-known principle known as Occam's razor, which says that everything else being equal, we must always go for a less complex hypothesis. In other words, we prefer models that are less complex. So the function f should be described using a less complex model. So if we are fitting a polynomial curve, then we should always choose a polynomial whose degree is small. Note that this is contrary to our stated goal of minimizing the fitting error or residuals. We have seen that we can drive the residuals to 0 if we take 8th degree polynomial. But that came at the cost of higher test error. Occam's razor dictates that if we can manage to obtain nearly equal fitting error, then lower degree polynomials are generally better. So then there is a trade-off between model complexity and the error. And this trade-off is depicted in this plot. So there are two plots shown here. As expected, the training error always decreases with the model complexity because the complex models can fit to the noise in the observations. However, as model complexity increases, the test error increases because the model fits more and more to the noise. As a result, you see two distinct regimes, and the aim is always to ensure that we pick the right model complexity that results in the best fit. For example, consider again the curve fitting example. If we were to choose an extremely simple model, such as the degree 1 polynomial, which is just a line, then it would obviously underfit and lead to a large training error. On the other hand, we have already seen that the 8th degree polynomial on 10 observations yielded a near zero training error but a very high test error. So therefore we can expect that a 2nd or 3rd degree polynomial would probably be the best and yield the smallest test error. Before moving on, I must mention that a caveat is that the shape of this curve is valid for general losses and training algorithms. For some specific losses and training algorithms, particularly in the context of neural networks and the stochastic gradient descent, the training process and the loss functions introduce artifacts that result in a different curve where basically beyond a certain point the test error starts to decrease again with the model of complexity. But such a behavior is specific to those losses and algorithms and is not seen generally. So in any case, I will not be discussing the double descent curve as it is out of scope, but if you are interested, you may have a look at the last reference here. So let us go back to the regularized least squares. Regularization provides us a framework for trading off fit with model complexity. The idea of regularization is that instead of only minimizing the empirical mean of the training loss, we add a penalty term. So here RF is the so-called regularizer, which measures the complexity of the function class f. In other words, RF is large when f is complex. We also have a parameter lambda that controls the importance given to the observations relative to the importance given to the model complexity. For example, if we set lambda to be close to 0, we are essentially ignoring the regularizer. So this problem becomes the classical empirical loss minimization that could overfit if n is small. On the other hand, when we set lambda to be large, we are giving a lot of importance to the model complexity and less importance to the data or observations. So if lambda is too large, we could underfit since the complexity of f would be too small. So ideally we want to choose lambda that is somewhere in between. A very common example of the regularizer in case of parametric learning is the Ridge-regression regularizer, where R is simply the sum of squares of the parameter values. For the linear least squares case, adding the Ridge regularizer still allows us to obtain a closed form solution because the objective is still quadratic in X. Further, we need not take the pseudo inverse in this case because addition of the regularizer makes the inversion possible. So u plus lambda I is always invertible in this case, and therefore the solution to this problem is unique. Intuitively, you can expect that the ridge regression penalty encourages the entries of x to be small because we are penalizing their squares. So the result will be a model, many of whose parameters will take small values. For the curve fitting example, we can see that compared to the ordinary least squares or OLS, the ridge regression yields a higher training error but smaller test error. In fact, as you can see, the green curve is much smoother looking than the blue one. There are of course many other choices for the regularization function, and one of them is the L1 norm regularizer. This particular problem is actually referred to as the lasso or least absolute shrinkage and selection operator. As compared to ridge regression, here we are penalizing the sum of absolute values of the parameters. Similar to ridge regression, lasso also gives higher training error but lower test error. We can see here that the lasso performs slightly better than the ridge regression, and the reason for that is that it yields an X star whose many of its entries are 0. So that is all about the regularized least squares and the various examples.